Okay. All right, so the deadline, the link to sign up for a presentation time is live. If you refresh the page, I did move the deadline to November 30th after we come home from break. It's a Calendly link. So if you sign up for a time, any one person in your group, please just take one time slot or else I got to remove you from the other time slot. Any person from your group, you can do your group name or just the name of anyone in your group. However you want to do that. I'll be able to figure out what you mean as long as it's somebody from your group's name on there. But if you have a name like Nick or something, please don't just put Nick, put your last name or something. Just give me enough information to be able to figure it out. So I'll give you a moment to talk with your group because I know you're going to anyway. I'm not going to try to talk over everyone. But I'll give you a second to sign up for a time if you're with your group and you're ready for that. And then I'll get started with lecture. Hi, Cole. Where'd the TAs go?
Take it whatever as late as we can get. Oh, late. Late as you can get it, bro.
It's the Oh, something I forgot to mention might be relevant in your decisions. If you choose one of these times before the deadline or even after the deadline, you don't have to have all of the features working in order to get full credit on your presentation. So if you do take that first Monday time slot and you don't have everything working, that's perfectly fine as long as you mention all the features and talk about where you're at in the project and follow the three sections, the demo, the architecture, and the advice to your future selves. I forget what I called that one. As long as you hit all those 3 points and cover everything well, you can still get full credit on the presentation. Even if you do it like the Wednesday during the final exam and you just weren't able to get everything working, you can still get full credit on the presentation. So keep that in mind if you're thinking about that Monday slot. You don't have to have the project done by your presentation time. Yeah. Yeah, the presentation is a completely separate grade. Right, so you go. Yes. Yeah, the project is the coding and reports, and the presentation is its own separate thing. Which, honestly, the presentation is like a free 10%. I don't grade those too harshly. As long as you show up and do what you're supposed to do, I'm not really grading too much on how gung-ho you went on it. Okay, everyone good? Signed up for a presentation time? There's also a Piazza, right? A Piazza post. I am looking for TAs for this course. Most of my TAs are graduating this semester. So there's a few slots that I'll hire for. So if you are interested, check out that Piazza post and fill out what you want there. I'm told that DARS reports aren't a thing anymore, so I'll update later, after lecture. But where I say DARS report, if you submit an unofficial transcript, that'd be perfect. I just want to know what courses you've taken. Like, for example, if you've taken distributed, that means you have more experience with Docker Compose, things like that. But let's get into this. So I thought I had more slides yesterday, but I actually did get through it all. I was rushing at the end a little bit, but we did get through all the slides. The only thing missing was an encryption demo. I don't really have much to demo. I guess I can run it real quick. Encryption example. So for this encryption example, I'm going to generate a key pair. I'm going to get my public and private keys, and then I'm going to encrypt the same plain text twice. I'm encrypting the exact same plain text twice, getting two different ciphertexts and printing them to the screen, and then decrypting and printing the two decrypted plain text back to the screen. I'm always going to decrypt back to the right value, the same value, but you notice my two crypto texts are extremely different. So if I'm sending the same message to you 2 times and they're both encrypted, those 2 messages are going to look significantly different. An attacker can't even gather any information out of this. They can't say, oh, these two texts that you sent were similar or they were identical. No, we're going to have that padding algorithm in there. These are going to be padded with different randomly generated paddings, and the crypto text looks completely different. They still decrypt just fine, but to the attacker, they get no information out of this crypto text. This is extremely secure. Even if we're sending a message with 1 bit of entropy, we are still secure. Encryption is very powerful, much more powerful than hashing, at least the way we use hashing. And the big difference is with hashing, we never want to go backwards. So we never go from your hashed password back to your password. We never want to do that. But with encryption, that is the normal mode of operation. We want to go back and forth. So we can hide all this extra entropy in the original message because we will go back and have a way to be able to ignore the extra information. That's exactly what we do with padding. So we have, encryption is a very powerful, it's secure as it can be. Whether you have 1 bit of entropy or 1,000 bits of entropy, it's secure because the algorithms themselves get to add extra entropy. Oops. Wrong browser. All right, we have all kinds of good stuff today to talk about as well. HTTP over SSL or TLS. Yeah.
I know that you mentioned before where it's maybe no pixels and everything, but I was wondering if you know any resources to learn more how do we do encryption when we're trying to work with applications and hashing.
How to do encryption? You mean just apply encryption or rebuild encryption, implement the algorithms themselves?
Both, I guess.
I guess I have the same answer for both. I don't have any specific resources off the top of my head. Just Google is your friend. Google around and find anything. I don't have anything specific off the top of my head. Yeah.
Is HTTPS just HTTP, but a little something extra?
Kinda. I mean, we're going to talk all about it. We're going to talk all about it. Yeah, kinda though. I don't want a big storm this weekend.
It's happening.
So So HTTPS, we very briefly introduced this last time. It's HTTP over TLS, commonly called HTTP Secure or Secure HTTP, which both are fine as well, but it is HTTP over TLS. So for this, the beauty of this, so all semester we've just been using HTTP. And late in the semester I'm saying, oh yeah, we're going to use this completely different protocol and replace all of your HTTP with HTTPS. But we're not going to have to rewrite any of your code. Everything you've written for HTTP, we're going to use all of it. All of it, and we're just going to slap this layer of security on top. So all of your HTTP code, in fact, whenever you write web servers, you're writing web servers in HTTP, and then you just add a layer of HTTPS on top. All of your code is perfectly valid. All of that code can be used in a secure HTTPS setting, and we're going to talk about how to do that. So the difference is that we have a layer of SSL or TLS. These days it'll always be TLS, and henceforth I'll just say TLS and ignore that it's ever SSL. But secure socket layer and transport layer security, when SSL, what would have been SSL 4.0, there's a little bit of, I just got to give a little bit of background here. When SSL 4.0 would have come out, when they came out with what would have been SSL 4.0, they decided to rename it TLS. So SSL, TLS, it's the same thing, it's the same protocol, it's the same libraries. They just changed the name along the way. So if you ever hear SSL, that's just an outdated version of TLS, or TLS is the new version of SSL, depending on how you want to look at it. But they're the same thing, they have the same goal, they accomplish the same things, but the newer versions just do it better. There was a reason why we got these newer versions, but I'll always call it TLS here. So it's HTTP over TLS, it used to be HTTP over SSL. So a lot of and the reason I even bring this up is a lot of the libraries and code that you're going to find, it's still going to be called SSL, like OpenSSL. If you heard of the Heartbleed bug, OpenSSL, which is the library we're going to use actually, they still call it OpenSSL even though it's implementing TLS these days. So it's important to know that history, just because if you're using an OpenSSL, you're actually using TLS. Everything's fine. You're not using an outdated version of things. They just didn't bother updating the name of the library when they moved to updating the name of the protocol. So a little bit of background. How this works, we're going to have to go back to our network stack for this. We haven't been at the network stack in a while, but this is what it's been looking like. We have our IP headers, and then our TCP headers, then our HTTP headers, and then the body of our HTTP request. So we got these three layers of our network all being implemented in our code right now. And we don't really think about IP in this course. In TCP, you use a library, you start a socket server, and let the library do your TCP stuff for you, the three-way handshake and all that. And then we worry about the HTTP layer. So now we're going to add this TLS layer right in between TCP and HTTP. And TLS is going to encrypt, it's going to work in the world of bytes, and it's going to encrypt and decrypt everything for us. So when we have the TCP layer in this stack, the TCP layer doesn't care that it just had this TLS layer above it that encrypted information, encrypted these bytes before sending it over the wire. TCP doesn't care. It just gets some bytes. These bytes happen to be encrypted, and it just sends those bytes over the internet. Doesn't care. HTTP, everything that you've written all semester, also doesn't care. You're going to send your responses. TLS is going to grab your response, encrypt it, and send it over to TCP. When we get bytes over TCP, TLS is right there to decrypt for us and then send us decrypted HTTP requests. Your code doesn't have to care that there's a layer of TLS in between you and your TCP socket. You just put that layer in there. All your HTTP code works just the same as it ever did. TLS does its thing, and then TCP works just as it always has in the past. Everything works just like it has, but we're adding a new layer into our network stack that's going to handle encryption and decryption. And this is what we like as developers. We write one thing, we write HTTP, everything, and then we just slap TLS on top of it at the end, and now, bam, we got HTTPS. That's why I like the name HTTP over TLS better, because it's more clear about what we're doing. It's not a new HTTP protocol. It has kind of nothing to do with HTTP at all. It's just adding a layer in front of HTTP to handle the encryption. So we could, I already said that. I'm going to say it right now. I have it on a later slide, but I want to say it right now. So we could actually go in the code when you create your socket. When you create your socket server, you can inject your TLS right there. You can write a few lines of code that's going to add a TLS layer, give it the public and private keys that you need or any encryption keys that you need for that, and have your server, or not your private key and your public cert. We'll talk about that in a bit. And then have that layer just do everything for you. Or what we're actually going to do in this course, the way I'll show you how to do it, is put a reverse proxy in front of your server, and the reverse proxy is going to talk TLS and then forward HTTP, raw HTTP requests to us, so you don't have to change a single line of code in your server. We're just going to add that layer in front of it. That's going to be in front of your TCP socket even, and then that's going to use your TCP and socket to send unencrypted requests to us, and your server works exactly the way it always has. Yeah.
So we want to send, say, just an HTML file. We open the file, we get the bytes object, we read all the bytes, we send the headers encoded, that string encoded, and we send
You do everything that you've done before?
same thing.
Everything. Everything's untouched. You don't even change your one single character of your code. It's all the same exact thing. But we're going to add a layer of TLS in front of your code. So let's talk about what TLS even is first, because TLS has a lot of nuts and bolts to it. Again, I mentioned this before, but this whole week I got a lot of background to show you of how to do that task, Objective 5 of your homework. I should call them either tasks or objectives in both 116 and 312. I have to keep switching between them, but objectives in 312. I got a whole week of background, and then when it comes to actually doing that in your code, there's not a whole lot to do. So a lot of this week is background, juicy, nice information to know, but you won't have to know the details of this in your homework. So whatever you'll do with that information, But this is how TLS is going to work under the hood. We're going to get Nginx to do all this for us, by the way. So what we want from this is two-way encrypted traffic. But there's a big problem with this, with what we have right now. We're going to have a server, your server with a private key and a public key. And then I'll talk about it at the end of this lecture. If it spills into Friday, so be it. But I might be able to get there today. A public key signed by a certificate authority, which is going to generate our public certificate that's made with our public key, that contains our public key. That's what we have. That's what we learned about on Monday, this public key encryption system. We have a public and private key. We can get a public key signed by a CA, which gives us a secure way to distribute our public key. And then whenever a user wants to send a message to us, they'll take our public key, encrypt with it, send it to us. We decrypt with our private key, and we can read that message. Cool. That's nice. We like that. It's okay. But how is your server going to send an encrypted message back to the user? Now, we could have the user generate a public-private key pair, send us their public key, but then every user is going to have to get their public key signed by a CA, get a certificate, and then send the certificate to us. A little bit of a pain logistically and just unnecessary, because we're going to see a better solution. So how are we going to get two-way encrypted traffic when all we have is a server's cert and the server knows its private key? How do we do that? So let's talk about it. TLS solves this problem for us really well. So the TLS handshake, we're going to negotiate how we're going to encrypt things for a particular connection. So we're going to agree on a symmetric, let me highlight this whole thing, a symmetric encryption key. This is something we haven't talked about before. I'm not going to go into much detail about it. You might have seen it in another course by now. But we want a symmetric encryption key, which is opposed to public key encryption systems. A symmetric key encryption system or symmetric crypto system uses one key for both encryption and decryption. So our server and our client are going to agree on a symmetric key that they're going to use for symmetric key encryption, and then they're both going to use that key to encrypt and decrypt. They both agree on this key, they both have the key, they both use it to encrypt, they both use it to decrypt. That's what we're going to get with TLS. So we want to securely agree upon a shared encryption key. So we have this challenge of having to agree on a shared secret. If we have any bytes of secret, if we have enough bytes of secret information that only the server and client know, we'll use that to generate a key. But we need to share a shared secret securely over an untrusted internet, where anybody can be sniffing packets out of the air and observing everything that we're doing. This is what we have to do. One way to do that, there are lots of algorithms to solve these things, but one way to do that I'm going to talk about is the Diffie-Hellman Key Exchange. For this, we're first going to generate, and it's math again, we're going to generate two numbers, one large prime number P and a number G, which is going to be a generator of the prime group P. There's a lot of abstract algebra. Man, I'm blanking on the name. There's a lot of abstract algebra that goes into this, a lot of these terms. Just very briefly, for G to be a generator of the prime group P, every value of I from 0 to P exclusive, G to the I mod P should be a unique value. This is going to be a generator, meaning that if we take G and keep multiplying it by itself, we're going to loop through all of the values from 1 to P minus 1. So this G is a generator of the group because if we keep multiplying it by itself, it will generate every value from 1 to P minus 1. It's possible to have values that are not generators, where you might go from like 2, I don't know why I'm even trying to do an example, like where you might not hit every value in that group. You'll end up looping around, you'll hit a repeat value, and then you just keep hitting that loop without hitting every value from 1 to P minus 1. So we want to make sure G is a generator, so we get the full volume of 1 to P minus 1, the full volume of this group. These are both public. Everybody gets to know those values, not hidden at all. Two values, the only two values actually, which will be hidden are A and B. A is going to be some secret number generated by the client, and B is a secret number generated by the server. These are very large secret numbers that we're going to generate and not tell anybody, including the other party. The server can't tell the client B, and the client can't tell the server A. These are extremely secret, only known to the server or the client, not both. Then some more math comes in. We're going to take that generator G, the client's going to raise G to the power of A mod P and send that to the server. The server is going to take that value and raise it to the power of B mod P, and they'll have successfully computed G to the AB mod P. Server is going to do the same thing, but with the opposite A and B. Server is going to compute G to the B mod P and send it to the client. Client's going to receive that value, raise it to the A mod P, and guess what? The client also has G to the AB mod P. And now they have a shared secret. Yeah?
Where is A stored? Like, is it encoded somewhere in the Chrome user data?
It won't be stored anywhere. Well, it's going to be used for this handshake and not stored. We don't need it after this handshake. You don't want to be storing those. Wouldn't it be TLS over HTTP? If you want to think of it that way, I guess. What is mod P? It means divide by P, and whatever the remainder is, you take the remainder. That's modulo math. Take some higher level math classes, you'll get to learn all about that stuff. So now they both have this shared value, which we're going to use either as a key directly or use those bytes to generate a random key. We might have another step to the algorithm that says take that shared secret and then apply this function to it to be able to generate our shared encryption key. but both server and client have that shared secret. So whatever method they agree upon, they're going to apply that to generate their key and have a shared symmetric encryption key, which will be the same for user and client. And the only information that was sent, the only private information, I should say, that was sent over the internet was G to the A mod P and G to the B mod P. G and P are public. Everybody gets to know those. And we have these two values flying through the air. So you have these values, G and P. You're an attacker, and your goal is to figure out either A or B. So if you figure out one of them, you can use the other value. If I crack this and I get A, I'm going to raise this value to A mod P, and I have the shared secret. So computing A or computing B is going to get an attacker to that shared secret, which we hopefully agree is bad because it breaks the internet. Had mod P, not mod P. I can't even see the difference. Mop. Just wanted to know what they were. Did I actually have mop P? I don't think I had. Oh, yep, right there. Mop P. That should be mod P, yes. Good catch. I didn't see that in my slides. So these are the two pieces of information that contain any private information. So if you can compute A or B from either one of these, everything's broken if an attacker can do that. Luckily, this is one of our cryptographic primitives that we talked about quickly at the end of last lecture. This is the discrete logarithm problem, which we all agree is quite difficult to compute to the point where as long as P is large enough, if we have a large enough prime that we're working with, then an attacker can't compute the discrete log of this value to generate what A is. They can't just take the discrete log base G of this and compute A. Can't do it, not before the heat death of the universe at least. Not going to do it. I didn't call these by name, but this is what we call a cryptographic primitive. Do I not have it on the slide?
You told it to us last month.
I didn't think I used the term cryptographic primitive, though. I use that on the next slide. But cryptographic primitive, factoring and discrete log, maybe I did, I don't remember. Factoring and discrete log, these are both called cryptographic primitives. So if you can reduce breaking your crypto system, if you can reduce that to breaking, computing factoring or discrete log efficiently, then you have a secure cryptographic system as long as the numbers are high enough. So if you prove, okay, if somebody can break my crypto system, they can use their method of breaking my crypto system to factor values very quickly, in polytime, we'll say. That's not quite accurate. But efficiently, we'll say. Then you got a good case for security, if you can reduce to a cryptographic primitive. So since this reduces to a cryptographic primitive, breaking this, it is directly discrete log. So you don't even have to write a reduction. It just strictly is computing discrete log. Done. So this reduces to a cryptographic primitive. Breaking the Diffie-Hellman Key Exchange reduces to breaking discrete log or computing discrete log efficiently. Therefore, we feel secure about it. And there are a handful of these cryptographic primitives where we just agree in the crypto community that these things are hard. We'll just say if you reduce down to one of these things, you're good. We got factoring, we got discrete log. These days, we also have elliptic curves and some math that we use with elliptic curves that reduces to brand new primitives that give us better security. Security that can't be broken by a quantum computer, at the very least. But I'm getting on a tangent here. So once we have a shared symmetric encryption key, we need a symmetric key encryption system. For that, the common choice here is AES is a good choice for that. It's nice and fast and efficient. So AES is kind of like how SHA-256 worked in a way in that it's a series of XORs and bits and a whole bunch of very low-level operations. So it's very fast. A lot of the operations are right in your CPU's instruction set. Very quick, very fast, but built in a way that you can undo it as long as you have this shared key. As long as you have the encryption key, you can run it backwards and decrypt with the thing. There are theoretical attacks to this. Since it doesn't reduce to a cryptographic primitive, it's just a whole bunch of XORs and stuff like that and shuffling up information. It's not strictly secure because it doesn't reduce to a cryptographic primitive, so it's not secure in that sense, but it shuffles things up enough that it's secure-ish. And there are theoretical attacks. There are papers written, and everybody got scared that AES is broken, but no practical attacks. Nobody's published a way to just really blow this thing wide open and destroy the crypto system. But theoretically, there are attacks that exist. So we're a little weary about using it, but, you know, it's okay. Yeah?
Theoretical attacks exist, and why haven't any of them been made yet? It's like been mathematical.
Because they're just theoretical. Like, theoretically, we can factor efficiently if we have a quantum computer. But it's not quite the same as that, but, you know, there can be theoretical attacks that you can dream up that just aren't practical. Like, if you have an algorithm that's, I don't know how much I want to go down this one. If you have an algorithm that's, I have to talk about too much background, but if you have like a polytime algorithm and you say, okay, I finally can solve this problem in polynomial time where it used to be exponential time, but your polynomial is n to the billion. You know, it's theoretically, okay, I can solve this optimally, but you don't have a practical solution to be able to do that. With AES, I think it's a little stronger than that. Like, it got a little scarier than that. I forget the exact details, but there is a paper out there that says technically we could break this in some certain way. I think it's only under certain conditions or something. I forget the details. But there are, you know, this might be on the verge of being broken, is the point of my bullet point, though. And DES, the precursor to AES, that one is quite broken. Don't use DES. For crypto systems, at least. It's still used in certain applications, but not for this. So the handshake, the mechanics of it, the client's going to send a hello, and that's going to say, here are all the algorithms that I support. The server's going to look at that list, compare it with the list of algorithms that it supports and that it prefers, and respond with its own hello, which says, these are the algorithms that we're going to use. The server sends its certificate. That's a key part of this. The certificate, we haven't talked about certificates yet, but the certificate is going to contain its public key, but in a verified way. And then they're both going to generate their parts of the symmetric key. That's A and B in our example. When the server sends its part of the shared secret, so when the server generates G to the B mod P and sends that to the client, it's going to sign that with its private encryption key. Sign it. It's going to sign it. It's going to say, I am the actual one sending this part of our shared secret, and then send it. Everybody has the cert for this server, so everybody can still read that part of their secret. Everybody has access to that information. It's just signed, but the client gets to verify that the server did in fact send that part of the symmetric encryption key. Client and server both have their parts. They compute the rest. They do the rest of Diffie-Hellman. And now they both have a shared encryption key, which they're going to use to encrypt messages back and forth. Now, in this whole process, that's the TLS handshake. Everything after that is going to be encrypted traffic with HTTPS. This whole process, we'll talk about certs. At this point, we probably won't get to it till Friday, which is fine. There's a lot of content in this lecture. But we'll talk about certificates and how we sign certificates and certificate authorities and root certificate authorities. A lot of work we have to do to take a public key and get a certificate for that public key. And the whole idea of public key encryption that we talked about last time, we generate a public key, a private key, there's math and cryptographic primitives, and there's a lot going on. Just for the server to have a private key and have a certificate that certifies their public key that they can share with everybody. We did a lot of work to set that up. And we said, we're going to use that for encryption, right? No. We don't use that for encryption. That whole thing, getting the certs and all that stuff, certificate authorities, never used for encryption, at least not for TLS, not for any practical applications out there, any common applications out there on the internet. Not even used for encryption. It's used one time right here, only to have a signature of their portion of the shared symmetric key for that session. We use it for one signature, and that's it. All that work for one signature so we can verify that this server actually did send us this part of the secret, the shared secret. That's it. We don't actually use that public key encryption system for encryption on the internet at all. We use it to agree on a shared symmetric key and then use that shared symmetric key to encrypt. Yeah.
So after we send all our bytes object, then HTTPS would then take over and encrypt it, and then that would be sent on the way out?
Yeah, TLS would encrypt it. Mm-hmm. So this gives us a lot of nice properties. The fact that we encrypt using this symmetric key encryption. One, AES is really fast. Like I said, it's mostly operations that are in your chip's instruction set. Very fast to encrypt, where public key encryption gets pretty slow, computing those exponentiations mod P or mod N. What letter do we use for that one? Gets a bit slow, but when it's all really minimal operations, quite fast to encrypt. So we do get some speed out of it also. But one big thing that we get is forward secrecy. What this means is that an attacker who wants to attack our crypto system and our cryptography and our messages and read those messages, they have to launch a live attack. This is forward secrecy. They have to launch a live attack, meaning they have to watch everything as it's happening in order to break any cryptography. So, for example, what they can't do, since we have forward secrecy, is monitor all of our traffic. They watch everything that's going back and forth, including the key exchange, the symmetric key exchange, all of that. They watch all of that information. They can't break anything quite yet, so they store all of that communication. They store all of that crypto text, and then later on down the road, this attacker breaks into the server, steals the private encryption key, and says, I got it. I'm going to decrypt all of that communication that we had that they sent back and forth. Can't do it. What can they do with that private encryption key? Nothing. It was only used for one signature. That was already public information. It was a signature, not a crypto text. They can't even decrypt that. They can't do anything with that. So all that information that they stored, they can't break it, even if they recover the server's private encryption key. They're SOL. They can't do anything with that. They can try to break the Diffie-Hellman Key Exchange and break it that way, but that's strictly a cryptographic primitive. A and B were never stored anywhere. They were thrown away. So they would have to break cryptography. They can't just steal the private key and do anything with it. They can't do anything with it. That's what we like. Forward secrecy. It has to be a live attack. They have to be attacking at the time. Actually, they can't even attack it at the time, the way I presented it there. Yeah?
Even if they like...
Or, yeah, they can. Oh, sorry.
It's just for a single TLS connection, right?
Yeah. So for every... And that's another thing. Every single TLS connection, even with between the same client and same server, you close your browser, you open your browser, you connect to that server again, it's a new encryption key. You're going through the key exchange again, you're getting a new symmetric encryption key every time. So even if they break one of those encryption keys, it's only one session that they can view. If you visit a page and you have like 5 different TCP connections with that server to make all of your requests, that's 5 different encryption keys. An attacker might if they break one of them, they only get that information. We like all these things as internet users and maintainers of servers. We like all this stuff. It's really hard for an attacker to break anything. They really have to break like the key exchange itself, being able to take those shared partial secrets and generate the shared secret. Then we're in trouble. But that reduces to a cryptographic primitive, so we're feeling okay about it. And I mentioned some algorithms here, RSA, Diffie-Hellman, AES. These were all mentioned in the example. These algorithms can be swapped out at will. So I use these ones as an example, and they're still commonly used out there. But you can use any algorithms you want. None of these are like hard-coded as part of TLS. TLS is very flexible and allows for any servers, any algorithms to be used or not used. You can add extra layers to this. You can remove some. TLS is a very, very flexible protocol that'll allow, it's meant to be future-proof. So when somebody does break AES, TLS doesn't have to be updated. You're just going to, in that client hello, server hello, you're just going to talk different algorithms. You're going to say, hey, I'm going to use this new algorithm that replaced AES. We're going to use that one now. I support that. The server's going to be like, cool. And if the client says, I only support AES, like in some future where AES is broken, the server's going to say, you only support AES and not the new stuff? We can't communicate. And it's just going to say, we can't do this. I'm not talking to you. So the protocol is really future-proof just by being able to hot swap these algorithms and supporting new algorithms in the future. So like Diffie-Hellman, if this becomes broken, we're going to replace this with, I think it's still Diffie-Hellman. I think it's still called Diffie-Hellman, but a key exchange based on elliptic curves instead of discrete logarithm like I presented today. We'll upgrade to that and say, OK, nobody's broken this one yet, and just switch to the new one. And we're constantly generating new crypto systems to be able to be ready for the next crypto system that's broken. Why would the client say, I communicate this way? Like, why wouldn't they communicate any other way? If you haven't updated your browser, for example, and your browser just doesn't have the code for the latest cool stuff. Would be one big reason. So just a note on this. Cryptography is great. We use HTTPS pretty ubiquitously on the internet now, ever since Chrome decided that they were going to show a warning if you're not using HTTPS. Kind of forced everybody to just get their certs signed and get their HTTPS going, get their TLS going. So it's pretty ubiquitous now, but we still talk about privacy on the internet all the time. So since TLS sits between TCP and HTTP, everything from HTTP down is going to be encrypted, or HTTP up, depending on which way you see your network stacks, is going to be encrypted, but it can't encrypt your TCP and IP headers. Can't do it. Mostly because these headers need to be used for routing. The IP headers especially. We can't encrypt IP headers because the routers of the internet need your destination IP address to figure out how to route this thing. If you encrypt the destination IP address, the first router is going to be like, I don't know, and throw away your packet. That has to be plain text. That has to be out in the open. TCP, once it gets to a machine, it needs to know which process to send it to, and that process is going to run its TLS to be able to decrypt that stuff. Maybe someday we can get TCP headers encrypted. That theoretically would be possible. We do it at the network card level. You know, that can happen. But IP certainly has to be out in the open. And the way it does work is all these headers are out in the open still. Destination IP, source IP, destination port, source port. All that information is out there in the open right now. This is why VPN still exists. This is why VPNs are still very popular. Even with encryption, since these headers are in the clear still, your ISP, anybody within Wi-Fi range, they can't see what you're saying, but like I can still sniff packets right here with Wireshark and figure out what websites you're visiting by looking at the IP, the destination IP addresses of the packets that you're sending. That can still happen. If I ever became like grumpy or something, or if I just wanted to know what's everybody doing while I'm lecturing, I could set up a machine that's just sniffing packets all lecture, and then look at all that information and see what websites you're looking at. And people out in the hall, I would end up getting them too. Maybe the classrooms next door as well. I don't care enough to do that. But that information is still out there unless you are using a VPN. Not sponsored, so I'm not going to mention any specific VPNs, but But that's why VPNs are still popular. That's how you can actually get more privacy that encryption can't offer us. VPN, for those of you who don't know, pretty much just bounces your traffic off another server. So I'd be able to see that you're connecting to a VPN, but I wouldn't be able to see what you're using that VPN, like what you're connecting to on the other side. So VPNs themselves, I don't want to go down the rabbit hole too much, but VPNs themselves, like the sites you connect to can still see that you're using a VPN in some cases. I mean, depending on your VPN, I guess, how complicated and tricky your VPN gets. But they can't see the other side of the communication. You can't see who you are, and on this side, I can see who you are, but I can't see who you're connecting to. All right, any questions? I'll save the whole certificate talk for Friday. But any other questions? Oh, lecture question. I didn't talk about certs. I can't do this lecture question, can I? It's going to have to be Friday's lecture question. Let me just redo the last one, I guess. Screw it. I'll just redo Monday's lecture question. Yeah, I just said that. This is Monday's lecture question. I'm doing Monday's lecture question again. Today's lecture question, I forgot. It was about certs, but I didn't get that far. So the lecture question you just saw is going to be Friday's lecture question. All right, have a great day. I'll see you on Friday.